Most parents assume a fancier computer means better learning. That's not how it works when you're 12. My name is Dr. Priya Mehta, and I'm a child developmental psychologist who specializes in how kids actually build STEM skills through hands-on work, not just screen time. You're listening to the STEM Lab podcast. Quick note before we dive in. Everything you're about to hear, the research, the data, the script, that's all been written and verified by real people. The voice you're hearing right now, though, that's AI generated. Just want to be upfront about that. If you've been listening for a while, thank you, really. And if you're new here, welcome. I'm glad you found us. New episodes drop every Monday, Wednesday, and Friday, so there's plenty more where this came from. Now, here's what we've got for you today. For most 12-year-olds, Arduino is the better starting point because it teaches fundamental electronics and embedded programming without the complexity of a full operating system. Raspberry Pi suits children already comfortable with computers who want to build software-focused projects. I'm going to walk you through the technical requirements, learning outcomes, expandability, and how each platform fits into progressive STEM learning paths. Let me give you the quick version first. Arduino focuses on embedded electronics, sensor integration, and physical computing. You program it using the Arduino IDE, which is basically C and C++, though there are block-based options through tools like MBlock or Scratch for Arduino. Screen dependency is optional. Many projects run standalone after you've done the programming. It draws power from 5 volts via USB or a battery pack, and it'll run indefinitely on its own. You expand it with shields, sensors, and actuators, though you're limited to what a microcontroller can handle. Starter kits run around $40 to $70. Raspberry Pi is general-purpose computing. It's a Linux-based system where you can build software projects. Python is the primary language, though it supports Scratch, JavaScript, C++, and full desktop IDEs. You need a screen for setup and most projects because it acts as a full computer. It requires constant power, 5 volts at 3 amps through USB-C, and it's not battery-friendly for field projects. You can expand it with hats, USB peripherals, cameras, and displays. It can run multiple processes at once. The board plus essentials will cost you somewhere between $75 and $120. Now let's talk about what your 12-year-old actually learns with each platform. The developmental difference centers on concrete versus abstract thinking. Arduino forces your child to understand cause and effect in the physical world. When they write code to blink an LED, they see the electron flow, the timing, the voltage states. That tactile feedback loop strengthens sequential reasoning. The Arduino Uno R3 remains the industry standard for embedded systems education because it isolates one skill at a time. Your child writes 20 lines of code to read a temperature sensor, and those 20 lines do exactly that. Nothing hidden, no background processes. This transparency builds confidence. They're learning embedded C++, the same language powering automotive systems, medical devices, and industrial automation. By month 3, most 12-year-olds can independently wire circuits, read data sheets for new sensors, and troubleshoot voltage issues with a multimeter. Raspberry Pi teaches computing architecture. Your child installs an operating system, manages files through terminal commands, and runs multiple programs simultaneously. The Raspberry Pi 5 with 8 gigabytes of RAM functions as a full Linux computer, which means they're learning system administration alongside programming. This complexity serves children who already grasp computer basics and want to build AI models, web servers, or computer vision projects. The screen time difference matters here. Arduino projects can run entirely offline after the initial programming. Your child codes a weather station that logs data to an SD card, deploys it in the backyard, and retrieves data weekly without ever looking at a screen. Raspberry Pi requires monitor interaction for nearly every task, though this does mirror real software development workflows. Concrete capability milestones for Arduino by 6 months include building autonomous robots with ultrasonic sensors, creating MIDI instruments, and logging environmental data for citizen science projects. For Raspberry Pi, you're looking at deploying basic machine learning models, building retro gaming consoles, and creating home automation systems with voice control. Moving on to the lab specs, power, connectivity, and infrastructure requirements. When you're evaluating these platforms for your home STEM lab, the infrastructure demands differ significantly. Arduino setup requirements are straightforward. Any computer running Windows, Mac OS, or Linux for the free Arduino IDE. The board draws 40 to 50 milliamps typically, spiking to 200 milliamps with multiple servos. Easily powered by a USB connection or a 9-volt battery for portable projects. No cooling needed. Storage happens on the board's 32 kilobytes of flash memory or external SD cards for data logging. Total desk footprint is about 12 inches, with a breadboard and components spread out. One honest friction point. Arduino's reliance on C++ syntax frustrates some children initially. Missing a single semicolon throws compiler errors that feel cryptic to beginners. The Arduino Starter Kit includes a projects book that scaffolds this learning curve, but expect your child to need support during the first few coding sessions. The screen isn't responsive or colorful. It's just a black text window with red error messages. This stripped-down environment can feel jarring compared to visual programming tools they've used before. Raspberry Pi setup requirements are more involved. You need a dedicated micro SD card, minimum 16 gigabytes, but realistically 32 gigabytes for comfortable use, a USB-C power supply delivering stable 5 volts at 3 amps. Underpowering causes random crashes that confuse young learners, an HDMI monitor, USB keyboard and mouse, and optional but recommended is an active cooling fan. The processor throttles under sustained load, which affects performance during AI training or video processing. Total power draw ranges from 3 watts idle to 12 watts under full load. Raspberry Pi demands network connectivity for most worthwhile projects. Installing packages, accessing documentation, and collaborating on GitHub all require internet. Arduino can operate completely offline after setup, which some families prefer for focused, distraction-free work sessions. Let's talk durability for repeated use. Arduino boards tolerate beginner mistakes better. Shorting a pin might blow that specific pin, but the board often survives. Raspberry Pi's delicate SD card slot breaks with rough handling, and corrupted SD cards from improper shutdowns frustrate learning momentum. I've watched my own daughter's Raspberry Pi project derailed by a corrupted file system after she unplugged it without running the shutdown command. That's an abstract concept for concrete thinkers. Now, expandability and the progressive learning path. The expansion trajectory shapes how these platforms fit into multi-year skill development. Arduino's expansion path follows component mastery. You go from breadboard prototyping to soldering shields to designing custom PCBs. Your child adds complexity through hardware, integrating water quality sensors, building renewable energy monitors, controlling stepper motors for CNC projects. Each new sensor teaches a specific protocol like I2C, SPI, or UART, building toward industry-standard embedded systems knowledge. Compatible platforms include Arduino Nano for wearable projects, ESP32 for Wi-Fi-enabled IoT devices, and Arduino Mega for projects exceeding the Uno's 14 digital pins. This modularity means your initial $50 investment in sensors and components transfers across board upgrades. The learning compounds. Skills mastered on Uno apply directly to professional development boards used in engineering firms. Raspberry Pi's expansion path follows software complexity. You start with Python scripts, move to Flask web applications, then TensorFlow machine learning, then embedded Linux development. The HAT ecosystem, that's hardware attached on top, adds cameras, displays, and motor controllers, but the real power lies in running desktop-class software. Your child can train neural networks, host databases, or run computer vision algorithms, projects impossible on Arduino's limited processing power.
The Pi bridges into professional tools naturally. A child writing Python on Raspberry Pi uses the same language, libraries, and workflows as data scientists. They can SSH into the Pi remotely, manage it headlessly, and deploy code through Git, real DevOps practices that transfer to software careers.
Consumables and subscriptions. Neither platform requires ongoing subscriptions, though both benefit from component restocking. Arduino projects consume resistors, capacitors, and sensors. Budget around $30 to $50 quarterly for active learners. Raspberry Pi projects rarely destroy components, but need USB peripherals, storage expansion, and occasional SD card replacement. Budget around $20 to $40 quarterly. Let's look at the software ecosystem and learning curve. The programming environment determines daily friction. Arduino IDE offers simplicity: one window, one button to compile and upload. The built-in examples teach by modification. Your child opens blink, changes the delay value, sees the immediate result. This rapid iteration cycle suits 12-year-olds' attention spans. Block-based alternatives like MBlock bridge from scratch, letting visual learners transition gradually to text-based code. The constraint becomes the gift. Arduino can't multitask like computers your child knows. They learn that while delay of 1000 pauses everything for 1 second, they need millis for non-blocking timing. This limitation forces computational thinking. How do I make my robot avoid obstacles while monitoring battery voltage while following a line? These are the concurrency problems professional embedded engineers solve daily. Raspberry Pi runs Thonny Python IDE, which provides friendly debugging and variable inspection. The full Linux desktop lets your child research documentation, watch tutorials, and code simultaneously. That mimics real development workflows, but also introduces distraction opportunities. You're essentially giving your child a full computer that happens to have GPIO pins. The learning curve steepens when projects require Linux terminal commands. Installing libraries through apt-get, managing file permissions, editing configuration files, these tasks build system literacy but overwhelm children expecting plug-and-play experiences. I've found that children comfortable with computers adapt within weeks, while those used to tablets and phones struggle with the text-based interface. Cross-platform note: both Arduino and Raspberry Pi run on Windows, Mac OS, and Linux. Arduino requires just the IDE download. Raspberry Pi needs separate setup even if your child owns a computer. It's a standalone device requiring its own peripherals, though it can be accessed remotely from a family computer once configured. So, who should choose Arduino? Choose Arduino for your 12-year-old if they thrive with hands-on, screen-limited learning and need to see immediate physical results. Children who enjoyed Lego Mindstorms or basic electronics kits progress naturally to Arduino's component-level work. It suits kinesthetic learners who disassemble toys to understand mechanisms and ask, how does this actually work? Arduino prepares children for electrical engineering, robotics, and mechatronics careers. The skills transfer directly to professional tools like PLC programming, embedded systems development, and industrial automation. A 12-year-old mastering Arduino today can contribute to high school robotics competitions, design custom lab equipment for science fair projects, or prototype inventions. Families prioritizing offline, focused work sessions appreciate Arduino's independence from internet connectivity and social media distractions. The platform teaches troubleshooting through physical observation. Your child sees the LED not lighting, checks the circuit, measures voltage, and fixes the reversed connection. This tangible feedback loop builds persistence better than abstract debugging. Who should choose Raspberry Pi? Choose Raspberry Pi for your 12-year-old if they're already comfortable with desktop computers and want to build software-heavy projects. Children who taught themselves Scratch or Python, enjoy gaming mods, or show interest in web development find Raspberry Pi's full computer environment familiar and empowering.
Raspberry Pi prepares children for software engineering, data science, and AI/ML careers. Your child learns version control with Git, manages cloud deployments, and works with industry-standard libraries like NumPy and Pandas. These aren't toy approximations, they're the actual tools professional developers use daily. The platform suits collaborative, internet-connected projects, building a Discord bot, hosting a Minecraft server for friends, contributing to open-source citizen science platforms. Your child learns to research documentation, troubleshoot through forums, and adapt code from GitHub repositories, essential skills for modern software development. Families comfortable with higher screen time in service of deeper computing literacy find Raspberry Pi worthwhile. Yes, your child sits at a monitor, but they're learning Linux administration, network protocols, and system architecture, foundational knowledge for technology careers. Let me address some frequently asked questions. Can a 12-year-old learn both Arduino and Raspberry Pi simultaneously? Yes, and many educators recommend this approach for accelerated learners, but it requires careful scaffolding to prevent confusion. Start with Arduino for 3 to 6 months to build electronics fundamentals and programming basics, then introduce Raspberry Pi for projects requiring more processing power or software complexity. Learning both platforms teaches your child to choose the right tool for each project: Arduino for real-time sensor control and battery-powered devices, Raspberry Pi for data analysis and internet-connected applications. The combined skill set mirrors real engineering workflows where embedded systems communicate with edge computing devices in IoT applications.
Absolutely. This combination represents professional IoT architecture and teaches system design thinking. Arduino handles time-sensitive sensor readings and motor control, while Raspberry Pi manages data processing, wireless communication, and user interfaces. For example, your child might build an environmental monitoring station where Arduino reads air quality sensors every second and sends data to Raspberry Pi, which logs it to a database, generates graphs, and uploads results to a cloud platform. They communicate through serial, I2C, or USB connections. This architecture teaches distributed systems, a core concept in modern software engineering, while letting each platform do what it does best. Which platform has better community support for young learners in 2026? Both platforms offer exceptional community resources, but they serve different learning styles. Arduino's community provides more beginner-focused tutorials, YouTube videos demonstrating physical builds, and forums where hardware troubleshooting dominates, ideal for visual, hands-on learners. The official Arduino Project Hub curates age-appropriate projects with complete parts lists and step-by-step photos. Raspberry Pi's community skews towards software development, with extensive Python documentation, Linux tutorials, and coding forums. Better for children comfortable reading text-based instructions and researching independently. The Raspberry Pi Foundation publishes free curriculum materials specifically designed for classroom use that parents can adapt at home, while Arduino's educational content focuses more on individual maker projects than structured curricula. Here's the bottom line. The decision reflects whether your child needs to master physical computing fundamentals or software architecture first. Arduino builds the electronics literacy and embedded programming skills that make robotics, IoT, and instrumentation comprehensible. Raspberry Pi develops the system administration and software engineering capabilities essential for AI, web development, and data science. Neither choice closes doors. The 12-year-old who starts with Arduino can add Raspberry Pi within a year as projects demand more computing power. The child who begins with Raspberry Pi can incorporate Arduino for real-time control when Python proves too slow for motor timing. Both platforms teach transferable problem-solving, debugging persistence, and project completion skills that matter more than the specific tool.
Watch how your child approaches problems now. Do they disassemble mechanical toys or prefer building digital worlds? That instinct guides your choice, and either path leads to genuine, career-relevant capabilities.
Thanks for listening to this episode of the STEM Lab podcast. New episodes come out every Monday, Wednesday, and Friday, so you won't have to wait long for the next one. If this was useful to you, I'd really appreciate it if you'd leave a 5-star rating and write a quick review. It actually makes a difference because that's how other parents and educators find the show. And if you haven't already, go ahead and subscribe or follow so you get notified the moment a new episode drops. I'll talk to you soon.